Bismillahirrahmanirrahim. Now our next theorem, that let U be a subspace of a finite dimensional vector space V over the field F. Then there exists another subspace W of the vector space V over the field F. Say that subspace, say W of the vector space V over the field F, such that vector space V over the field F is the direct sum of the subspaces U and W. Suppose since the set U is a subspace of a finite dimensional vector space V over the field F is a finite dimensional subspace of the vector space V over the field F. Let the set A consist the element U1, U2 up to UM of the vector subspace U of the vector space V over the field F is a basis of the subspace U. Then this set is by definition of the basis this set is a linearly independent set in this subspace U of the vector space V over the field F. This set can be extended to the basis of the vector space V over the field F by adjoining the vectors W1, W2 up to Wn of the vector space V over the field F. That is, the set B, which is the superset of the set A, consists all the element of the set A as well as the new element W1 up to Wn, which this resultant set is a basis of the vector space V over the field F. And that is the elements W1, W2 up to Wn are also linearly independent vectors according to the definition of the basis, and the subset C consists only the element W1, W2, Wn of the set B is also a linearly independent set in the vector space V over the field F and is span a subspace W of the vector space V over the field F. That is, the elements U1 up to UM span the subspace U of the vector space over the field F, and these are the elements of the this is the these are the element of the vector space V over the field F, which are these are the element of the basis of the vector space V over the field F, and is this set the element consists these element U1 up to UM is a subset of the basis of the vector space V over the field F, and that set span the vector space U, which is a basis for the subspace U of the vector space V over the field F. Therefore, the remaining element of the basis of V, that is W1 up to Wn, also span another subspace of the vector space V over the field F. That subspace is denoted by W. These elements are linearly independent because these are the element of the basis of the vector space V over the field F and are linearly independent. By a theorem, the subset of linearly independent set is linearly dependent. According to this condition, according to this theorem, this is a subset of the set B, and each element in the set B are linearly independent. Therefore, this subset of the set B is also linearly independent and is generate the subspace W of the vector space V over the field F. Therefore, the set C is a basis of the subspace W of the vector space V over the field F. As U is a subspace of the vector space V over the field F, and W is another another subspace of the vector space V over the field F, which we generate from the element of the basis vector of the vector space V over the field F, from those elements which are which do not generate the subspace U of the vector space V over the field F. These are two subspaces of the vector space V over the field F. Therefore, the sum of these two subspaces is again a subspace of the vector space V over the field F. And also the set B the set B contain all the element of the set A, and the set B is a basis of the vector space V over the field if this is a basis of the vector space V over the field if, that is these elements generate the whole vector space V over the field if, also as well as these elements, the set B, the element of the set B which are from U1 up to UM are the element of the set A, and from W1 up to Wn are the element of the set C. That is the set B is the union of the set A and the set C, and generate the sum of the subspaces U and W, because the set A generate U and the set C generate the subspace W. Therefore the union of these two sets gives a set which generate the sum of the subspaces U and W. That is, this set generate the vector space V as well as generate the subspace U plus W. Therefore the vector space V over the field F is a subspace of the sum of the subspaces U and W. From equation first and second, the vector space V over the field F is equal to the sum of the subspaces U and W. Also is the set A span the vectors the subspace U, and the set C span the subspace W, and the set B span the sum of the subspaces U plus W as well as the as the vector space V over the field F. That is the element span U and the element span the subspace W. There is no common element, that is the intersection of A and C is empty. Therefore therefore only the zero vector is common in these two subspaces, and from the result V is the sum of U plus W, and U intersection W is equal to zero vector. We combine these two results, we conclude that the vector space V is the direct sum of the subspaces U and W.